My name is Amir. I work for InterSystems for 15 years. I started in Brazil, then moved to Chile, now I'm here. So my English will be a little bit weird. You may not understand something. If that happens, please let me know. How many of you have worked with Spark already? So that's good, because I'm just learning as well. So what I'm going to try to do for you is what I would love to have once had done for me. Okay, so I learned this thing a little bit. I'm still learning, and it's very confusing sometimes. So I'll try to give you the key points and try to make it easy, as I would love someone had done for me. So this is the agenda. We are going to talk a little bit about the Spark architecture and IRIS architecture, like how both of them work together, and possible IRIS and Spark configurations, like how we can put Spark to work with IRIS in different configurations. Some basic concepts that will be useful when we start looking into the code, and a demo, a real thing that we're going to poke around. So first, Spark is a big data compute engine. Spark is about processing data. It's not about storing data. So Spark doesn't care about where the data comes from. It can come from Hadoop, it can come from a big CSV file, it can come from IRIS. So Spark is perfect for us because it's about computation. It's about processing large amounts of data. And it brings lots of libraries for training machine learning models. That will be our focus here, but also for doing other things: statistical analysis, data exploration, stream processing, talking to machines. So it's kind of an adapter as well. So Spark is built in Scala. It's a functional language that runs on a Java virtual machine, but it allows you to write Spark code in many other languages. You can write your Spark code using Scala, Python, or even Java. So there is this driver process. That's where your program is running. That's where your code is. So as I said, let's suppose we are writing this on Scala. The first thing we do when we are writing a Spark program is to open a session. And that session is how you talk to the Spark cluster. And the Spark cluster has a master and at least a single worker. But normally you have like several workers. And those orange boxes there, as you can see, are in different machines. So we can leverage parallelism in several different machines with lots of cores, lots of memory. And everything stays in memory. So when Spark reads data from somewhere, it will store it in memory and split the data into all these servers. So a piece of for instance, you have like a million records table, and we have here 3 workers. You end up with 300,000 to 33 million in each box in memory. Okay? So where the data comes from? In this case, from IRIS. As I told you, Spark doesn't care where the data comes from. It can come from Hadoop, it can come from a CSV file system. In this case here, it will come from IRIS. Okay? And you can even mix. For instance, sometimes you're taking data from IRIS and merging it and joining it with data from a CSV file, from streaming that is coming through TCP IP. So you can merge data while we are working too. So for Spark to access the data in IRIS, we have a Spark connector, right? And the Spark connector allows each worker to independently connect to IRIS and fetch the data. So you can start with a single IRIS instance. Like I just have one database. I don't have sharding. I don't have. You don't even need mirroring. You know, just a database. A single iris database can hold lots of data, as you can know. Like we have there easily, I don't know, 50 million records on a table, and you want to train a machine learning model on it. It will work. You don't need sharding for that. But if you need to, if you really have really big data, you can use sharding, and we'll take advantage of that. We use the parallelism of sharding. So some configurations. The traditional configuration you will find out there very frequently on the internet is that you have Hadoop as your persistent storage, and people work with CSV files. Okay, so they will have an ETL process that will export the data from, I don't know, a database, and put on some files in Hadoop. Hadoop is just a distributed file system, and it will spread these files on many servers so that the file may be very big, and you distribute that file on many servers. But with IRIS, it's direct access. We don't need Hadoop. You can use Hadoop because sometimes you do have like a file that is coming from somewhere else. It's not coming from IRIS, it's coming from another system, and you're using Hadoop as your file system. That's fine, but you don't really need it. And Spark can connect directly to IRIS. And it can connect to your mirror backup machine. So while the primary machine is working with the transactional application of yours, Spark is reading data from the backup. So you can actually work with Spark on your current data from the last second without any performance penalties. You can do that also with ECP. So for instance, if you're using enterprise cache protocol, you can work on the database server, preferably on the backup server, while ECP is doing the transactional processing. You can also use Spark for ETL. For instance, sometimes you do have a database, you want to bring data into IRIS. Spark can connect to that other database and easily create a table on IRIS for you and bring you all the data. So it's very convenient for ETL. And during this process of bringing data from other database into IRIS, you can create transformations and fix the data, select only what you want, apply several Spark functions before inserting the data into IRIS. So I'm almost finishing this PPT. My idea is to get into the demo and see the Spark working, but we need to understand some concepts. I just want to emphasize that a typical configuration of IRIS may start like that. Like we have a database server, right? It can be mirrored and have high availability, and you may have some computing nodes with enterprise cache protocol to distribute your concurrent access, your transactional users. And you can add Spark when you need it. Like I want to train a machine learning model right now. You start a Spark cluster, point to your IRIS instance, do your job, and then throw it away because it doesn't have state. Spark will fetch the data from IRIS, do this processing, and when you have a model, you can throw everything away, and you don't have to keep the Spark cluster running unless you're doing streaming. But if all you want to do is to train a machine learning model, do it, and then kill the cluster. So you can scale your transactional processing here. You can scale with sharding your data volume, like store more data on your database, and you can scale independently Spark as well. If what you're doing is very heavyweight, you can just add more Spark workers. So it's very convenient, and you don't have to keep paying for that hardware. If you're using the cloud, for instance, or running on virtual machines on your own data center, do your job and then kill the cluster. You don't have to keep it up. So some concepts. RDD, the Resilient Distributed Data Set. That's the core concept inside Spark. That's just a distributed table, okay, in memory. So I load, as I told you at the beginning, if I have like 1 million records and I'm loading that from IRIS, and I have 3 workers, what will end up happening is that 1/3 of the data will be on each worker. And that's all in memory. Okay? So when you have your program there that you wrote in Scala, in Python, or in Java, and you created that Spark session, you can apply transformations to that data. So you just connect it to IRIS, loaded that, 1 million records, and what do you do next? You apply transformations to the data. You look at the data. You filter it. You drop some columns you don't need. I don't know. But these transformations, they are only triggered when there are an action. So for instance here, I have some Spark code. That's the one that's working, right? I told him that I wouldn't walk, but as it's so close to me, there is a Spark code here. And what this is doing is, this is a data frame, and I'm filtering all the lines that have IRIS on it. But that didn't do anything to the cluster, because I didn't ask for the data. So it's there. It is waiting for me and waiting for an action. So now what I want to do after filtering all the lines, I want to count. And that will trigger the work. So now the cluster is working. And it started by filtering on each worker the lines that has IRIS on it. And then it starts on each worker counting the results. And on the Spark cluster, it will do the final sum of count. So on each worker gave back its count. And on the Spark cluster, the cluster master, it will do the final count. So now that's the concept of lazy processing. So you can actually add lots of instructions like filter that and filter this other thing and convert that to uppercase, and it will be doing nothing. Only when you tell him like, show me, or count, or I don't know, it will start working. We'll split the work between the workers and start working. And you don't even need to think about the order. Like, maybe it's more efficient to filter the lines that has IRIS first and then convert them to uppercase, right? Because I would be working on a subset of the data, uppercasing a subset of the data. You don't have to think about that. Spark is smart enough to understand that he must invert that and do the mapping first and the filter later. So let's see something now. How much is that? Perfect. Okay. So what we are going to see, I built a demo with Nitor, is a partner that has helping me with the machine learning models that we are putting into our demos. And they gave me the machine learning code in PySpark, and I converted, in Python, not using Spark. And I did a very crappy job converting it to Spark. So if you see the code, please don't blame Nitor. They did an amazing job. So we have transformers, 18,000 transformers. And that's a real use case. And every transformer gives us a signal every minute about its temperature, vibration, oil, temperature, several data points from that transformer. We have IRIS receiving these signals, and the idea here is that, for instance, the vendor of a transformer, they will tell you, don't need predictive maintenance, because I can tell you that from a year from now, you have to do this. You have to change the oil, I don't know, add more oil every so and so. They have this schedule like sorted out. But you kind of do predictive maintenance. There are some anomalies that can happen. Some transformers, for instance, may be under the sun, others can be under the rain. A bird may have built a nest on it. I don't know. Things can happen, and the idea is to find these anomalies before something really bad happens. But as the transformers are operating on different locations, under different weather conditions and so, every transformer has a personality. So the idea here is to find anomalies. So to find anomalies on a specific transformer, we need to train a model for that specific transformer. So it's a very interesting problem, because instead of training a model using all the data and treating all the transformers as if they were the same, we are building a model for every single transformer. So it's very, very cool. So the signals are coming in, and I will walk again, because it's so close. And IRIS will look at the signal and realize, oh, this is transformer 001. So I will pick the PMML model 001 and pass the signal through it and see if there is an anomaly or not. If there is an anomaly, I will start alerting and starting workflows so people will act before these things go wrong. And after I'm done analyzing this signal, I will store it on an IRIS archive database. And that's where Spark kicks in. Spark will access that archive database, and we will look at all the data and upgrade and improve our machine learning models. And new PMML models will be generated and fed into the service layer. So now this service layer can keep smart, right? They can keep track of changing conditions. So I am about to start a cluster using Docker and Docker Compose on my machine, and we will have 1, 2, 3, 4, 5, 6 containers running. So there is the IRIS interoperability container that's receiving the signals and doing everything that I just discussed, and then it archives the signal on the IRIS archive database. It's another instance, it's another container, and it could scale independently, use sharding or not, you get it. And then there is a Spark cluster that I am starting 2 workers, so you can take a look at how it looks like. And we have Zeppelin, a notebook that data scientists use a lot, that you're going to see that we use that to interact more friendly with Spark. We could also work with Spark on command line, but through Zeppelin, you'll see that's a lot more friendly. So let's do that. Get out of there. Okay, let me see. Okay, the cluster is already started. I let it up. So you'll notice here, I must be careful of this coffee, that I have all these colors here. Those are different containers telling me stuff. Okay, they're all up. So we're not. Oh, I'm sorry. Let me fix that. Thank you. So display, arrangement, mirror. That's it. Okay, so that's what I was showing. I was just showing that these different colors you see here on the left are messages from all the containers I just started. Okay, and I have my web browser here, and I'm looking at the service layer. So here you can see the transformer, the business service that is receiving the signals from all these transformers. And if you click here, it will tell you what he's doing with those signals. And there is this process here that is running the anomaly detection machine learning operation that will take the right model and apply it to the data and give this process a response. And this process will fire an alert and start a workflow with the maintenance team if there is an anomaly. Okay? And finally, we archive the signal on the archive database so that the data scientists can keep the models current. If I click here on the archive signal, you'll see that I have a JDBC connection to the archive database. So it's a real thing. And machine learning model here, it's a business operation that I wrote that just takes the PMML model. It doesn't have any configuration here. I can configure a PMML model like a fixed one for all the data points. But what I'm doing here is that the PMML, the machine learning model, will be picked based on the request I'm receiving, based on the data that is coming in. Okay, enough of this. Let's see what we have here. These are the signals that are coming, and I don't know if maybe I should. I think it will start. Maybe I just pick an old example. Well, but I can make a message pass through here, and we'll see when a signal comes in, something like this here, and we'll explore that. And this is the process. I'll not spend a lot of time here, but that's how we orchestrate all this work. So I can call the machine learning model here. I have an if the threat is bigger than 0, I will start an alert. I'll send an alert, call the maintenance team, wait for a report from them, and then archive the signal on the data lake. So let's see Zeppelin. Well, no, before seeing Zeppelin, let's look at the Spark cluster. So the Spark cluster has a web page like this, and as you can see here, I have 2 workers on different servers, and they are doing nothing. They are alive, but they have 1 gigabyte of memory each, and they haven't used any memory yet. You can see here too that I gave each worker a single core and 1 gigabyte of memory. So my entire cluster has 2 cores and 2 gigabytes of memory. So that's cool, because imagine like if you had 10 workers, each worker with, I don't know, 32 gigabytes of memory, you would see here what? 320 gigabytes of memory. And I don't know how many cores, the total number of cores you're using for your processing, and what is running, and how long it's taking. So we'll come back here. So let's go to that Spark notebook, to the Zeppelin notebook. So this is where we normally work with Spark. I will open another notebook here first, the introduction. So this is me looking at the data. I'm a crappy data scientist. I just wanted to put something beautiful here for you to see. It may make not much sense, but I found this beautiful, and it just relates the oil temperature with the transformer power load. So if you're doing more work, you're getting hotter, and you'll see that on the graph. So the data makes sense, right? And I'm just using JDBC here, okay? So there is nothing special. I can look at the data like that, or like as a graphic, and now I broke my graphic, but that doesn't matter. And now we can start with the anomaly detection and really use Spark. So here is the same thing now with Spark, and I will zoom here so you can look at it. So that's the data frame. I'm using PySpark, so this is Python with Spark, and I'm reading data from IRIS, and that's the table, and the table name, load, and I just want 100 records. And I can show it, and it will appear like that, because that's built for the command line. But the Zeppelin notebook can make that data frame here look beautiful. like the JDBC before us. So we can use Spark to fetch the data from IRIS and look at it in a very easy way. And here is Z is the question was, what is this Z object? The Z object is a special object from Zeppelin that has some utility methods like this, like the show, that takes a data frame and give all these buttons here. It's very convenient to explore your data frame. Okay. And it also works with arrays, with dictionaries, basic data structures. So it's really very convenient. Scala is the main language. Spark was built with Scala, right? So here I have the same thing in Scala. Now I have to use an import to get InterSystems Spark connector. I need to use vol here because I'm creating a value, a variable. It's a data frame, and I'm reading data from IRIS. And I'm using the same Z object to display that data frame. So as you can see on the same notebook, I can use, you saw here, I use PySpark, I use JDBC, I use Scala with Spark. There are many languages. I don't want to confuse you. If you are just learning this and you know neither Python or Scala, I really had a better experience with Scala because I'm more like, I like typed languages. But if you are more like untyped, go with Python, and the same documentation of Spark will work for both. Okay, so just pick the language you like. So let's pick that notebook let's build a model, right? So here I'm importing several libraries and to train our machine learning model, and I will run this. So I can hit play here. Well, let's just hit play. It takes a little bit of time. The first time that I run something, creating that session, connecting to the cluster takes some seconds, and then it's more faster. This text here, I can double click, and this MD here tells Zeppelin that this is a markdown. So I can start taking notes and like, okay, that's what I'm doing, that's my theory, I'm going to do this and that. And you can share that with your co-workers. So it's very convenient. You can put your conclusions here. What am I doing? And I just saved it, and I can see it now like that. So this just imported here, and here comes the fun part. Now I'm using Spark with Scala, and I'm reading an IRIS table. As you can see here, I'm doing a select, and you may think that this select is being sent to be run on IRIS. That's not the case. Okay, Spark has a SQL parser. It has a SQL engine, and he's asking IRIS is for the data. Like, I need this data, and the cast, the functions you apply here they are run on the Spark cluster. They are not run on IRIS. IRIS is just here is the data, the raw data. Okay, so that's important thing to understand. I'm telling Spark to cache that data in memory. So because sometimes it will just, okay, you're not using this data frame any longer, I will just throw it away. But I want to keep it in memory. And I'm counting it, and I have 8,000 records. That's just a demo. We don't have a lot of data. And then here I just asked it, well, I didn't, in fact. It's not, but you got the idea. I was asking asking Spark to drop any rows that had new values, because that sometimes causes problems to the machine learning processing. I'm showing the data. We already saw that, right? We have like the transformer load, oil temperature, and several other data points. I'm trying to understand a little bit of the data, making some sense of the data. So here you can see a filter. So I'm asking to that data frame, filter all the columns that have a threat greater than 0. So up to this point, it did nothing, right? Remember, it's lazy execution. Only when I'm running the count is that it fired this to the worker nodes. And now I'm calculating how many records I have that has a threat level greater than 0 compared to all the other records I have. So it's just 4%. 4% of the records have an anomaly. And that's sometimes they say that this is like an unbalanced data model. It's an unbalanced data, I'm sorry. And what that means is that I have too many examples of the good thing, like a well-behaved transformer, and too little of the bad thing. So when I'm training the machine learning model, what he will actually learn is how to recognize, good behaving transformers, and not the transformers with anomalies. And I want just the opposite. So sometimes, depending on the machine learning algorithm you're using, you have to do something about it. Okay. In our case, I'm using a decision tree, and that doesn't cause many problems. In fact, I don't really care if this machine learning model works or not, because you know that I'm a crappy data scientist. I just want to show you Spark, right? So, well, feature selection. What data points are important? I have all these fields, but what data points really tell me if there is an anomaly going on or not? I don't know. There are algorithms that I can apply that can tell me, you know what, you don't need to care about oil temperature. I do, in fact. But it has no relationship to the threats, to the problems you had in the past. So don't worry about using it when you're training your model. So that's another thing they do when they are analyzing the data. And that's all here on the Spark Notebook. They can work and compare notes and share this. It's a web application. The data scientists can share this and work together on this model. Well, now we're seeing a more complex function. What this does is it receives a data frame and a transformer code, like transformer 001, transformer 002. And a pipeline. You see more in the code that a pipeline is the way I train a machine learning model. So look at this pipeline as this is the magic. This is how I train the machine learning model. So I have the data, which transformer to consider, and the machine learning algorithm that I use to train the model. So the first thing is to ask the full data that I just received here, to filter it by the transformer. I just want data from that transformer. Remember, transformers have personalities. I'm creating a machine learning model for each transformer. This is very particular to this problem. So now I have the data for that specific transformer, and I'm splitting it into two random sets. I want 70% of the data on one data frame, and I want 30% of the data on another, because I will separate some data for testing what I just trained it. Okay? And then I'm fitting the training data. And that's that easy. Like I have that algorithm, and I need to fit it to train it using that training data. And I got a model. I have the training model in my hand. And now I can make some predictions. So I ask the model, apply what you have learned to the testing data. And I got predictions. It's another data frame with predictions. And now here this evaluator, what it does is to test if my predictions are, for instance, I have a field on my record that says, this record was threat level 2. And what have you, model, predicted? I predicted level 2. Okay, so this is working. And if it predicted level 0, okay, that's a false negative. And it will give me an accuracy. And I am just printing this accuracy here. And finally, I'm exporting this model to PMML, to a file. Okay, and that's it. So here I'm getting the list of transformers. I'm going to IRIS again, and I'm going to another table now and getting the list of transformers. I have only 5 transformers. This is the schema of the data. Why am I displaying this? Because some fields here have, I don't know, string type, Boolean type, and this all must be converted to integers. So I need to do something about that. So what I'm going to do, and another thing is that when you're running the pipeline, it expects a data frame that has a vector of data points. So I'm using this class here. That's very common. That's a very useful. That's a very common pattern. Okay, when you're training machine learning models, the vector assembler, what it does is it will take my data frame and pick these columns here as input for my machine learning model, and create a vector called raw features with all these data points. So I will have a single, one data frame that has this single column, and on that column I will have an array of data points. It's just weird that they need that, the data in this format. So it's just creating a new column for us with all the data that we want. The vector indexer looks at the raw features and creates another column called features. And what it does is, okay, oil temperature, this is an integer. It's a continuous value. Okay, I would just pass this as is to the features array. Threat level, or I don't know, let's say city where the transformer is. It's a string, so this is not an integer, so I can't work with that. So what vector indexer does is to transform that into an integer. So first it takes all the cities you have and creates a lookup table and then gives you the integer for each city. And it does that for you automatically. And this chi selector here is very cool because it helps you to look at all your fields, all your data points. Because remember, you have a threat level there, like this transformer is exploded, this transformer exploded, this transformer burned out. You have that field that tells you that something happened to that transformers and how the signals were. And what it does is to try to find correlations between the data points and that threat level. So, but looking at all the data, so for instance, it will take transformer load, top oil temperature, bottom oil temperature, oil volume, and we'll try to look at the threat and see if there is a correlation. And it will only leave me with the top 4 most important features. So I don't have to use all the features to train my model. That's a lot more cheaper than using all the features. So I'm building this, and now I'm building a decision tree. So this is the algorithm, decision tree classifier. And I'm telling him the column that tells you if there is a problem or not is the column threat. And the features that you have to look into is in the column selected features. So I have an array of integers there, remember? And I create a pipeline, and I set the stages. So the pipeline will start with the vector assembler that will take the data from my data frame that I took from IRIS, transform that into a vector of integers or strings vector. And then vector indexer will transform the strings into integers, doing automatic lookup tables for me. The chi selector will filter and leave me only with the features that are most important. And then I run the model classifier. So it's a pipeline. And now I have a for loop that goes over all my transformers and calls that that function up there, and it gives that function all the data and the transformer code that I'm looping on, the pipeline that I just created, and this is used to name my file, the PMML file I am generating. So I have to run all of this. I forgot to keep running it, so let's do that. So this is fast. Oh, I have a problem here. Okay, I have to go up and create. So I'm loading the data frame. I am counting it again. As I hit play here, there is a status here. And what is this? Do I need that? Yeah, now it worked because the data frame wasn't loaded. So only 4% of the data is a thread. And now we have that function and the transformers. I could hit play here and run the entire notebook, okay? And that's the schema. And now we are going to train the model. So that is going to take a while. Oh no, that's the basic infrastructure, and here is the train the model. So now it's working. And you can see here, training model for transformer 001. And if we go to that page here and refresh it, we'll see that we have an application running that's called Zeppelin. That's a notebook connecting to the Spark cluster. And both workers are working and using their full memory. I'm using all cores, all memory from both my workers. I could jump into one of those and see what is running there. I can have more executors. So those are threads or jobs that are running on that machine, on that worker machine. I could have many here. I just have one. I can come back to the master cluster, and it's still running. We can come back to the Spark, and it's printing me all the accuracy of these models and generating the PMML files for me. The cool thing here is that these PMML files are being imported by IRIS in real time. So the data scientist just created a model, and IRIS just picked it up and is applying in real time. IRIS has now, you can see here on the right of the screen, that importing file. All these PMML files that I'm generating from the other machine, from the Zeppelin machine, IRIS is taking and importing it. The question is what PMML stands for. PMML means predictive machine modeling language. That's my English sometimes. But it's an XML language that allows you to export machine learning models. So I generated the model using Spark, and now I'm using in IRIS. Knittor, for instance, created a model in Python, and they exported to PMML as well, and I could use it in IRIS. So the data scientists can pick the language they like to create a model. I'm just happen to be talking about Spark here. So this PMML file could have come from anywhere, and if we search here, for some reason there is no messages coming in, but I know this demo keeps sending me signals, okay, but it's not working. We'll not lose time with that. Let's pick this one here. So I have the transformer, and that's a record that just came in. That's the data points, and that's the process. And I'm calling the machine learning model. If you look here, I have all the features as numbers. There are no strings. And I have the model that I want to run. This is the model for transformer 009. And I have an answer now, and it tells me that this is the prediction for probability of threat being No, yeah, prediction is 1. I'm sorry. Yeah, here it is. Prediction 1. A threat can be 0, 1, up to 5. 5 is like this, it's in flames already, it's exploding. So 1 is like something is going wrong. And that generated an alert. So an email will be sent. And a ticket to the maintenance team has just been opened. Okay. I'll just stop here because we have only 0 seconds. And I wanted to see if you have any questions. I can show the PMML file so you can see how it looks like. I will just, what I would do to do that is to stop this service here that keeps importing it. And I will run that. I will run that training again, and it will, oh, no, not this, this. Okay, and it will generate the PMML files again, okay? The first is file, it's a file adapter, it's just looking at the folder. Oh, this one here? I'm sorry. The first. This is, this is code I wrote to call the PMML model. There is no adapter. No, but there is no adapter. Because it's running inside IRIS. Okay, it's, we have IRIS can run, can import your PMML, and it's translated in object script. Okay, it runs inside IRIS. So we should have by now some files there, and we could look at. These files are being left here. No, transformer signals. Okay. So am I still loading them? No. So I can go there through here too. So please, if you have more questions, IRIS demo. All the source code of these demos will be released. Okay, so you'll be able to look at this more in more detail. And also, I'm having a session by the end of this day on the Flash Talk about. I'm doing a deep dive on these demos, like showing the Docker containers and showing the code. Yeah, here we have. It's today, 4 p.m., the session. So I don't know why they're not appearing here. I have to refresh. Oh, here. Yeah, there. That's how a PMML looks like. If you see here, from all the features I had, it picked only the transformer load, top oil temperature, and oil volume as predictors for the threat level. Okay. Well, thank you.